Ever felt like we're hitting a wall? With technology, I mean. Like our phones are fast, our internet is speedy, but some problems, they just laugh in the face of all that processing power. What if the very foundation of our digital world isn't just slow for those problems? What if it's wrong? A complete paradigm shift needed. Because the questions we're asking now? They require something truly different. Something that doesn't just calculate faster, but calculates differently. This isn't about incremental upgrades. This is about rewriting the rules. For decades, it's been simple, right? Ones and zeros. Bits. The bedrock of every single device you touch. Your phone, your laptop, even the smart fridge judging your late-night snacks. It's all just switches, flicking on or off. Billions of them, doing one thing at a time, incredibly fast. And it works. It built the internet, powered AI, let us binge-watch cat videos for days. But what if those fundamental on-off switches, those binary bones, hide a deeper, more profound reality we've barely tapped into? A hidden dimension of computation. Imagine trying to map every single possible interaction between, say, just 50 different molecules. Not just one interaction, but all of them. The permutations. The probabilities. A classical supercomputer? It would take longer than the age of the universe to even scratch the surface. This isn't a speed issue, it's a fundamental architectural limitation. Some puzzles are so intricate, so vast in their possibilities, that our current tech hits an impenetrable wall. We need a new kind of calculator. A new way to think about everything. For centuries, we thought the universe was pretty straightforward, right? Big things, small things, all playing by predictable rules. Then came the whispers. The unsettling observations from the incredibly tiny world. A place where particles don't just exist in one state, but many. Where cause and effect get murky. Where certainty is a quaint old myth. And what if we could harness that uncertainty? That inherent weirdness? Not just to observe it, but to compute with it? To build machines that speak the native language of reality itself. Forget bits. Meet the qubit. Sounds like a sci-fi villain, doesn't it? But it's far stranger. While a classical bit is either a 0 or a 1, a qubit can be both. Or neither. Or somewhere in between. Simultaneously. It's not magic, it's quantum mechanics. This property, known as superposition, means a single qubit can hold an insane amount of information compared to a classical bit. Think of it like a spinning coin before it lands. It's heads, it's tails, it's everything, all at once. Until you look. Why is this both at once thing such a big deal? Because it's not just one qubit doing it. Imagine multiple qubits, each existing in a multitude of states simultaneously. The possibilities explode exponentially. 2 qubits can be in 4 states. 3 qubits, 8 states. 50 qubits? That's more states than there are atoms in the observable universe. Instead of trying every single path one by one, a quantum computer, using superposition, can explore all paths at the same time. A truly mind-bending leap. As if superposition wasn't enough, there's another quantum weirdness, entanglement. Imagine 2 coins, miles apart. You flip one, it lands on heads. Instantly, impossibly, the other coin, without being touched, also lands on heads. They're linked. Connected in a way we can't fully grasp. Einstein called it spooky action at a distance. In quantum computing, entangled qubits share a fate. Measure one, and you instantly know the state of the other, no matter the distance. This isn't just communication, it's shared destiny. So, what happens when you combine superposition and entanglement? You get a powerhouse. A computational engine unlike anything we've ever conceived. Not just faster, but fundamentally different. It's like comparing a bike to a spaceship. Both move, but one warps reality to get there. This allows quantum computers to tackle those unthinkable problems: drug discovery, material science, cracking impossible codes, simulating complex systems with unprecedented accuracy. It opens doors we didn't even know existed. But the how is where the real struggle begins. This all sounds amazing, right? Like we're just about to unleash a technological singularity. But there's a catch. A huge catch. Quantum states are incredibly fragile. Think of it like trying to hold onto a whisper in the middle of a rock concert. Any vibration, any stray light, even the slightest change in temperature, and those delicate quantum states collapse. Poof. Gone. The superposition vanishes. The entanglement breaks. It's called decoherence, and it's the ultimate party pooper of quantum computing. To combat decoherence, we have to create the most isolated, coldest environments known to man. We're talking temperatures colder than deep space. Like, way colder. Close to absolute zero. Specialized refrigerators called dilution refrigerators cool these tiny quantum chips down to millikelvin ranges. They look like steampunk chandeliers, but they're essential. This extreme cold slows down all molecular motion, minimizing vibrations and thermal energy that could disrupt those precious qubits. It's a technological marvel just to keep them alive. But it's not just about cold. It's about silence. Absolute, profound silence from the outside world. Quantum computers need to be shielded from stray electromagnetic fields, vibrations, even minute air currents. It's like putting the most sensitive microphone in the universe inside a vault, then inside another vault, then burying it under a mountain. We're fighting against the very fabric of our environment, which constantly tries to look at our qubits and force them to pick a single, classical state. This isn't easy. Even with the deep freezes and the isolation, errors happen. A lot. Quantum systems are inherently probabilistic, which means mistakes are not just possible, but expected. And fixing them isn't like classical error correction, where you just flip a bit back from 1 to 0. You can't just look at a faulty qubit without collapsing its delicate state and destroying the information. So, quantum error correction is a whole new beast. It involves using many physical qubits to encode one logical qubit. It's wildly inefficient. This brings us to the biggest bottleneck: scaling. Right now, quantum computers have tens, maybe a few hundreds of qubits. But to tackle truly world-changing problems, we need thousands, even millions of stable, interconnected qubits. And with current error correction techniques, you might need 1,000 physical qubits just to create one perfectly reliable logical qubit. Imagine the infrastructure. The power. The sheer engineering nightmare of linking millions of these fragile, supercooled, isolated systems together. It's a monumental challenge. You might have heard the term quantum supremacy. Sounds like a sci-fi villain's evil plan, right? It just means a quantum computer performs a specific task that no classical supercomputer could possibly do in a reasonable amount of time. It's a benchmark. A proof of concept. Google claimed it in 2019. But hold your horses. The tasks are usually highly specialized, not general purpose. It's like building the fastest car for one specific, super weird racetrack. It doesn't mean it's ready to replace your laptop. Not yet. Building the hardware itself is a monumental undertaking. Different types of qubits exist: superconducting, trapped ions, topological, photonic. Each has its own pros and cons, its own set of mind-bending engineering challenges. Fabricating these tiny, perfect structures, keeping them stable, controlling them with exquisite precision, it's like trying to perform brain surgery with oven mitts on, while riding a unicycle in an earthquake. The level of precision required pushes the absolute limits of materials science and microfabrication. So, we have the theory, the potential, and the absolutely bonkers engineering challenges. But what about us? Are humans the ultimate limit? Our understanding of the quantum realm is still evolving. The very act of observing these phenomena changes them. We're trying to build machines based on principles that even the greatest minds struggle to fully grasp. Is it possible our intuition, our classical way of thinking, is the ultimate barrier? Can we ever truly understand something that defies our everyday experience? Or will we just build it and hope it works? Even if we conquer the hardware, there's the software. Programming a quantum computer isn't like coding your smartphone app. It's a whole new language, a whole new way of thinking. You're not just giving instructions, you're manipulating probabilities, designing quantum circuits, thinking in terms of interference and amplitudes. We need quantum algorithms, clever ways to exploit superposition and entanglement to get the answers we need. It's not intuitive. It requires a different kind of genius. A new generation of programmers. Despite all the progress, fundamental questions remain. What is the true nature of reality at its smallest scale? Can we ever fully bridge the gap between the quantum and classical worlds? Are there limits to what quantum computers can theoretically achieve, even if we overcome every engineering hurdle? Maybe there are problems so profound, so complex, that even the universe's own computational fabric can't untangle them. The rabbit hole goes deeper than we can imagine. And we're still just peering over the edge. What if quantum computers aren't just about faster calculations? What if they unlock entirely new forms of intelligence? New ways of understanding consciousness? Or even, as some theorize, provide a window into other dimensions or parallel universes? This isn't just about building a better calculator. It's about fundamentally altering our relationship with information, with reality itself. The potential is as terrifying as it is exhilarating. Are we ready for what we might uncover? For the secrets it might reveal about our existence? So, where does this leave us? On the cusp of something extraordinary, but with monumental obstacles. Quantum computers are not replacing your laptop next year, or probably even in the next decade. They are specialized tools for specialized problems. But the journey itself, the relentless push against the limits of physics and engineering, is profound. It's forcing us to rethink the very nature of information, computation, and reality. And that, perhaps, is the greatest breakthrough of all. The understanding that the universe is far stranger, far more powerful, than we ever dared to imagine. We're just at the beginning of understanding these machines. The limits aren't just technological, they're conceptual. How far can we push the boundaries? What truly is the computational ceiling of the universe? And when we finally hit it, what will we have become in the process? Will we transcend those limitations, or will we find ourselves humbled by the ultimate mysteries that even quantum computers cannot solve? The answers lie not just in circuits and cryogenics, but in the deepest questions of existence itself.